let's remind ourselves, give ourselves a review of the comparison test, see where it can be useful, and maybe see where it might not be so useful, but luckily we'll also see the limit comparison test, which can be applicable in a broader category of situations. So we've already seen this. We want to prove that the infinite series from n equals 1 to infinity of 1 over 2 to the n plus 1 converges. How can we do that? Well, each of these terms are greater than or equal to 0, and we can construct another series where each of the corresponding terms are greater than each of these corresponding terms. And that other series, the one that jumps out at, that will likely to jump out at most folks, would be 1 over 2 to the n. 1 over 2 to the n is greater than, and all we have to really say is greater than or equal to, but we can actually explicitly say I'll just write it's greater than or equal to 1 over 2 to the n plus 1 for n is equal to 1, 2, all the way to infinity. Why? Because this denominator is always going to be greater by 1. If your denominator is greater, the overall expression is going to be less. And because of that, because each of these terms they're all positive, this one, each corresponding term is greater than that one, and by the comparison test, because this one converges, this kind of provides an upper bound, because this series we already know converges, we can say, so because this one converges, we can say that this one converges. Now let's see if we can apply a similar logic to a slightly different series. Let's say we have the series, the sum from n equals 1 to infinity of 1 over 2 to the n minus 1. In this situation, can we do just the straight up comparison test? Well, no, because you cannot say that 1 over 2 to the n is greater than or equal to 1 over 2 to the n minus 1. Here, the denominator is lower, means the expression is greater, which means that each of these terms can't provide an upper bound on this one. This one is a little bit larger. But on the other hand, you're like, okay, I get that. But look, as n gets large, the 2 to the n is going to really dominate the minus 1 or the plus 1 or this one has nothing there, it just has 2 to the n. The 2 to the n is really going to describe the behavior of what this thing does. And I would agree with you, but we just haven't proven that it actually works. And that's where the limit comparison test comes in helpful. So let me write that down. Limit comparison test. Limit comparison test. And I'll write it down a little bit formally, but then we'll apply it to this infinite series right over here. So the limit comparison test tells us that if I have two infinite series, so let's say this is going from n equals k to infinity of a sub n, and I'm not going to prove it here, we'll just learn to apply it first. And this goes from n equals k to infinity of b sub n. And we know that each of the terms a sub n are greater than or equal to 0. And we know each of the terms b sub n are, actually we're just going to say greater than 0. It's actually going to show up in the denominator of an expression. So we don't want it to be equal to 0 for all the n's that we care about. So for all n equal to k, k plus 1, k plus 2, on and on and on and on. And this is the key. This is where the limit of the limit comparison test comes into play. And if the limit as n approaches infinity of a sub n over b sub n is positive and finite, is positive and finite, then either both series converge or both series diverge. So let me write that. So then that tells us that either both converge or both diverge, which is really, really useful. It's kind of a more formal way of saying that, hey, look, if as n approaches infinity, if these have similar behaviors, then they're either going to converge or they're both going to diverge. Let's apply that right over here. Well, if we say that our b sub n is 1 over 2 to the n, just like we did up there, 1 over 2 to the n, so we're going to compare. So these two series right over here, notice it satisfies all of these constraints. So let's take the limit the limit as n approaches infinity of a sub n over b sub n. So it's going to be 1 over 2 to the n minus 1 over 1 over 2 to the n. And what's that going to be equal to? Well, that's going to be equal to the limit as n approaches infinity of 2. If you divide by 1 over 2 to the n, that's just going to be the same thing as multiplying by 2 to the n. So it's going to be 2 to the n over 2 to the n minus 1. Over 2 to the n minus 1. And this clearly, what's happening in the numerator and the denominator, these are approaching the same quantity. And actually, we can even write it like this. Divide the numerator and the denominator by 2 to the n if you want. Although it's probably going to jump out at you at this point. So limit as n approaches infinity. Let me scroll over to the right a little bit. If I divide the numerator by 2 to the n, I'm just going to have 1. If I divide the denominator by 2 to the n, I'm going to have 1 minus 2. I can just write this 1 over 2 to the n. And now it becomes clear. This thing right over here is just going to go to 0, and you're going to have 1 over 1. The important thing is that this limit is positive and finite. Because this thing is, so this thing right over here is positive and finite. The limit is 1. Is positive and finite. If this thing converges and this thing converges, if this thing diverges and this thing diverges, well, we already know this thing converges. It's a geometric series where the common ratio is less than 1. And so therefore, this must converge as well. So that converges as well.